Welcome to the course on two-dimensional signal processing, principles and practices. Today we'll look at the discrete cosine transform, one-dimensional as well as two-dimensional, how we extend that one-dimensional DCT to two-dimensional DCT. Though there are many types of DCT, we'll look into one even symmetrical DCT. How do we get it through the DFT, the background what we have, by the process of computing this to 1D DCT is as follows. Suppose the sequence given as x of n, which is of n points, n number of samples, and to compute this DCT, what we do is create an intermediate sequence, that is y of n, which is having two n points. Like n point, 2n point should be there in y of n. How do we get this 2n points? How we are going to make this y of n signal? We'll see through it, and then compute the DFT of this 2n point, that is y of n, and then get the y of k, that is the frequency domain signal of the y of n, that is y of k, that is also having 2n point here, because of this is 2n point, and this would also be having the DFT results in 2n point. From that 2n point, we would going to collect only n points of DCT, that is the cxk, which is collected. So how we are going to collect this, and how do we make this n to 2n point, we'll see them. And this cx suffix xk is the DCT coefficient of x of n what we had taken. So we need to form an intermediate sequence, and then taking the DFT. From the obtained DFT, we multiply by some coefficients, and then we get the DCT coefficients. So taking this, how do we make x of n into y of n? So x of n is the sequence, and we have x of 2n minus 1 minus n. That's a mirror image of this x of n needs to be formed to and add these two. So then we get y of n, that is x of n as such we take for the length 0 to n minus 1, and then from n samples, n minus 1, from nth sample onwards to 2n minus 1, because we need the length of 2n, and to make the mirror image of this x 2n minus 1 and minus n. So we'll see that example with n equal to 4. So in that case, how do we form this y of n? So for the even symmetrical DCT, and y of n is midpoint symmetric at n minus 1 by 2 for n equal to 4. So let's say take this is the sequence x of n, which has 0, 1, 2, 3 samples. The rest of them are zeros. Okay, so if this is x of n, and how do we form y of n for this? So x of n, repeat this for 0 to 3 indices, n from 0 to 3 indices, same thing, and then take the mirror image of it, which is computed from 2n minus 1 minus n. So this is 4, and this would become 8 minus 1, 7 minus n is the x, 7 minus n is 0, that would be x of 7. So this would be copied here, and 1, that would be 6. So here, and then 2, this is here as 5, and then the 1 is 3, 4, 7 minus 3 here 4. So this 2 will be symmetrical. So we get the mirror image which is symmetrical about n by n minus 1 by 2. That's the center is at n minus 1 by 2, the midpoint symmetric signal. So this is the way in which y of n is obtained from x of n. The same way we would do it in the 2D DCT as well. This is in one dimensional. We just take the mirror image, and this is one in n1 direction. Similar thing we'll do it in the n2 direction as well in the two dimensional DCT. So this is even symmetrical DCT to compute that. So we got y of n. Now take the DFT of this sequence, that is 2n point DFT 0 to 7, that is 8 point DFT we have to take in this case. So if we can also get the x tilde of it, that is if you see the x of n, which is made as repetitive sequence of this period 4, you can see the discontinuities over here. Okay, so there is a sudden discontinuity in the periodic sequence. Similar way, if we take y tilde from y of n, so in y of n, this discontinuities are avoided. Actually, the even symmetrical DCT, there is no, like there is a case of discontinuities. So that contributes in the energy compaction property. So it is used in the image coding as well when we do the two-dimensional signals of the examples with image. Then the coding examples, we can see that this especially DCTs are used in that case. So these are getting x tilde and y tilde, which avoids the discontinuities. So after obtaining this 2n samples of y of n, this one, then we compute DFT of y of n. So n is varying from 2n minus 1, it's not n minus 1 samples. So take the 2n samples DFT, that is w suffix 2n kn. So we have here this wn is e power minus j 2 pi by n. So this 2 which is representing is a w suffix 2n can be seen. So taking the 2n point DFT, that is now y of n is x of n plus x of 2n minus 1 minus n. So w2n k kn. So where the n is summation is varying from n0 to 2n minus 1. So this sequence y of n what we had shown over here, and now split that this one here for simplification and getting this y of k expression also. So n is varying from 0 to n minus 1, x of n, w to the first part, this portion is just n point, like n point DFT. So the other one from n here, n to this is 4 to 2n minus 1. These samples, the red ones, are x of 2n minus 1 minus n w2n kn. So now taking this DFT, how can we simplify this further to get the expression of y of k? So if we take this portion as p, consider this as p, and what is n from this? Obtain n, which is going to be 2n minus 1 minus p. So now what is the limits, how the limits are getting changed? So when n equal to n, so what is the p value? So p is going to be giving n minus 1 here. So when n is a 2n minus 1, and what is the p value? It is 0. So the summation now would change from, for an index of p, 0 to n minus 1. So this summation can be now represented with xp, and p equal to, here n is p equal to 0 to n minus 1 and xp, and here this n now replaced with 2n minus 1 minus p. So all this together, now we can change this, because these are all p, this p can be again changed to here what we have is n. So this replaced with n here, and then this is n equal to 0 to n minus 1. So we have this p is replaced again n. So this summation remains as such, that is, there is no change in the first summation. This is the y of k, the 2n point DFT we are computing in the DCT. Okay, x of n, 2k this portion, and this is over here, and this is the p is changed to n. P can be replaced with n because this now terminologies have been changed here. So now simplifying this, this becomes 1. So e power minus j 2 pi 2n to k 2n. This would cancel, this would result in 1. So this remains same, and this summation now x of n, and these two terms exist. So this becomes 1. So minus of n plus 1 we can have into k. So for the simplification, the 1 x of n w suffix 2n kn is now multiplied by 1, and that 1 is now splitted into this way, x of to just for the simplification, w 2n 2n minus k by 2 and plus k by 2. If you add these powers, you would get this as 1, and the 1k into n plus 1 is now, this 1 is splitted into here minus k by 2 and minus k by 2. So if you add it, this is minus 1 and minus k into n. So the last term there. So for the simplification, if you take this common term here, minus k by 2 is in both here, you can take out an n x of n, and this becomes, that is n plus 1 by 2 into k, and similarly here minus k and n plus 2. So the difference is only plus and minus here. The summations are the same after this simplification. So now this equation is one sum, you can bring it in one summation. N is varying from 0 to n minus 1, x of n having this. So what is this? This is going to be e power minus j 2 pi k into n plus 1 by 2 by 2n. So this term is now, we know this. So two terms here we can represent this is one, this is plus and this is minus here. So we get minus and plus. We can replace this as a 2 cos term, e power j theta. So 2 x of n cos of 2 pi 2n, all of them would come k into n plus 1 by 2. So the simplification, now we can see the DFT equation is simplified to, there is a coefficient of course. After this x of n, instead of this basis function in the DFT, now it has become cos of 2 pi 2n k into n plus 1 by 2. So this is the equation of the 2n point DFT what we got. So from this is valid from k 0 to 2n minus 1, and now we have to as a last step collect it only 0 to n minus 1 samples. So for that what we get is multiply this with, if you replace this by this side, so you would get 2n k by 2. So the rest of the term is going to be cxk, that is the coefficient, and it's only for first n coefficients 0 to n minus 1. So y of k, what we get this c, from that we can obtain cxk. This is the DCT coefficient. Multiplying this y of k with w2n k by 2 would result in a DCT coefficient, and that is only for the first n samples of in the DCT coefficients. It is 0 otherwise. So this is to obtain the DCT coefficients of 1D. Like take the x of n, steps can be if x of n, and then make y of n, and then compute 2n point DFT of y of n, and from that y of k collect only the n points for the DCT coefficient. If x of n is real, this coefficient would also be real. If x of n is complex, then it would also, cx would also result in complex values. Now the inverse DCT, as we did through one process in computing DCT, so we can get the cx coefficient from yk. That is, how do we get this? That is the cxk coefficient to be extended to yk, and then yk should be changed to y of n, and then we get the y of n to xn. So that means here we cxk, first we got the cxk, that is the DCT coefficient. From this DCT coefficient, how do we get y of k? So like we did in the even symmetrical case, so the y of k is obtained. This is n points only, we have to get 2n points here. So as y of k is always the 2n point, so multiply the cx coefficient by minus k by 2 of Tudel factor 2n, and if that is for 0 to n minus 1, and the 0, the center midpoint k value is n equal to 0, and then it is repeating that mirror image we get as we did in the time domain, cxn 2n minus k here into minus of 2n k by 2. So if we multiply this by knowing only this and get the mirror image 2n minus k, and the coefficients plus and minus, so we form the y of k of 2n points again. So 0 to n minus 1 and n, and then n plus 1 to 2n minus 1. So this is now the y of k, and from this inverse DFT should be applied to get y of n, and 2n point you will get in the inverse DFT. So inverse DFT is y of k. You can see the Tudel factor which has minus, so e j 2 pi k by n, where n is 2n here. So this summation varying from k 0 to 2n minus 1. This is the inverse DFT equation, that is IDFT equation for k varying from 0 to 2n minus 1. So once obtaining this yn, then we have to get only the x and n points from it and discarding the other n points. So from this y of n, what we have got, and x of n is collected only for 0 to n minus 1 samples, the rest of the samples are discarded. This is inverse 1D DCT. So x of n, if we take after collecting, that is how do we obtain 1 by n, k is varying from 1 to n minus 1, it should be k equal to 0 to n minus 1. So the k equal to 0 component is taken separately. So cxk, that is a coefficient, the cos of pi by 2n k into 2n minus 1, this is the basis function, cxk, and multiplying it from this. So k equal to 0 component is taken separately to get the x of n, and it is 0 otherwise. So this term cx 0 by 2 is generalized as wk, and wk is taking some values, different values for k, which can be described as k equal to 0, this is taking 1 by 2, this coefficient, and k equal to 1 onwards, it would take only 1. So x of n can be obtained from its DCT coefficients with coefficient wk, cxk cos pi to n k to n plus 1, varying from k is varying from 0 to n minus 1, that is the inverse DCT. So we have to keep in mind that for DC coefficient, that is k equal to 0, this Wk is different. This is not the Trudel factor W, this is the W coefficient which is used for the constant value used for the computation here. So the DCT pair can be described as follows, that is 2 x of n cos pi by 2n to k 2n plus 1. This is to obtain the DCT coefficient from x of n, and if you know the Cxk, you can obtain the x of n from this inverse DCT through that. So this would remain same here. We can see the factor which is Wk, as I told, that is going k equal to 0, this is 1 by 2, otherwise this k will be 1. Okay, so 1 by n is a DCT samples which we are going to take. So the obtaining this through forward 1D DCT and then the inverse DCT is the process which we had learnt. So Wk would take these values, and to summarize this 1D DCT, step 1 is to get y of n from given x of n, and then step 2 is to get the DFT of this y of n, that is 2n point, and then getting DCT coefficient as collecting the y of k as W 2n k by 2, that is multiplying this coefficient would result in DCT coefficient, and it is 0, otherwise this would be only n point. So in between we will use it for 2n points, and inverse DCT, so having this y of k or the Cx of k, get y of k, that is step 1, and the y of k, how do we get it, is for n minus 1 samples and n plus 1 to 2n minus 1. This is the way from available coefficient we would get the mirror image of it, and then take the inverse DFT of y of k. This is 2n point DFT computation. After that, step 3, we collect only the n points, that is from y of n, which is x of n. There are 3 steps to compute the DCT and 3 steps to compute the inverse DCT as well. So this is one type of DCT, that is the even symmetrical DCT, which is popular and mostly used. So we take an example through the code, just a simple code to just describe that. So we take x, there is a signal which is of cos 2 pi by 40, and which is also having frequency change, which is varying 1 to 100, and there are 1 to 100 DC is also added with that low frequency sequence here, input signal x. So that means this signal amplitude is also slowly growing, and this signal is also having a DC for 1 to 100, which is 100 points, it will be slowing. So it's a drifting sequence of low frequency. So that in that sequence, if we take a DCT of it, so this capital X is DCT X, this is a 1D DCT. So we get and plot it with the 2 subplot, that is 2 1 comma 1 here, and plot X, this is plot the sequence, input sequence, and the 2 of 1 comma 2 plot the DCTs what we obtained. So from that we get the plots. So this is the sequence, input sequence, and the second one is you can see the DCT coefficients obtained for this. Suppose this is 100 points here, and for the 100 points of the sequence, and here you can see that it is having the DC, this sequence, and its amplitude is also, it's slowly drifting. Okay, so it's a slowly drifting sequence if you keep plotting it, and the DCT coefficients more or less are in the up to 7-8 samples only, and rest of the coefficients are 0. So that this is the energy compaction property of the DCT, where all the coefficients of this sequence is lying in the low frequency region. Okay, can we successfully recollect or reconstruct this input sequence from this DCT coefficient? That is through the IDCT, that is inverse DCT. So if we take that, taking x and the DCT, and then what we do is we collect from this DCT coefficient 20 points to 100 points, we make it 0, and take only first to 20 points having some values, and rest of them make it 0, though those values are very small, and we make it 0, and then try to take the inverse DCT. Okay, so of this sequence we get the plot. We would see that m is from 0 to or 1 to 20 values. Okay, and then can we successfully reconstruct x or not? That's what we are trying to say. And then next one, from m2 we make it 20, instead of 20 we take it 10. So 10 to end, that means these coefficients we made it 0, x of this one, and rest of the coefficients are there. So first to 1 to 10. So in that case, taking this IDCT f(x), can we reconstruct it or not. We plot it and show that. And similarly, in the next case, we also made M3 8, that is from 8 to rest of the end sequence, make it 0. Can we successfully reconstruct it or not? And the next case is from 7 to end. We make the coefficient. So we keep reducing the coefficients which we are using for reconstruction process. First we had taken first 20 samples, and then first 10 samples, and then first 8 samples, and then 7 samples, and then we also do it for 6 samples. Okay, and we see them for these cases, and also for first 5 samples alone for reconstruction. Remaining are zeros. So purposely made it 0, whether we are able to reconstruct it, and what is the energy compaction of this DCT. So if we take only m equal to 20, yes, this is perfect. It's okay to, I mean, we got the original sequence, that x, small x, the drifting sequence, fine. That is for first 20 coefficient, we use it for reconstruction, inverse DCT. And then for first 10 also fine. There is a small change here in CY, you can see that, but it is okay that we could get the sequence. And for next 8 coefficients also, this could be reconstructed, or the original signal can be obtained from the DCT coefficients what we had considered. And the m equal to 7 from here to here, and this is also okay. First 7 coefficients also we could use for reconstructing the sequence. But when we go beyond that, that is first 6 coefficient only, this is failing to reconstruct. I mean, we are not able to get the sequence, original sequence here, that is x, small x. And similarly, if you go further, 5, only use 5 coefficients, and this is just completely failing to get the signal back. So this way we can see that the coefficients or the signal energy is only in the first few coefficients, that is up to 7. So the remaining coefficients are not useful, and we made it 0, you can see. And but 6 and 5 has some coefficients. So the energy is fully concentrated in the low frequency regions. That is what we are trying to say from here. So the basis function, if we understand, this is cos pi k by 2n to 2n plus 1, which is used for the correlation of the sequence and the x of n and this to get the DCT coefficient. So when we want to extract fundamental, second, and so on, so here it is plotted for 50, n equal to 15, k is varying from 0 to 7. So k 0, 1, 2, 3, 4, 5, 7 is given here. K equal to 0 is DC, and this would k equal to 1, not as in the case of DFT, or we can say unlike DFT, k equal to 1 is not giving the fundamental. You can see k equal to 2 is representing the fundamental, which is because of this factor. And similarly, k equal to 3 is completing only 1.5 cycles, and k equal to 4 would complete the 2 cycles. Okay. And similarly, that k equal to 6, it is having 3 cycles completed. So if you want to extract fundamental, then we need to use here k equal to 2 in the case of DCT. If you want to extract the second harmonic, then you have to use k equal to 4 instead of 2. So that's twice of it. As in the case of DFT basis function, these are the two things. This 2 pi k by n, for same n equal to 50, k is varying from 0 to 7, k equal to 0 gives DC, and k equal to 1 gives the fundamental, second harmonic, third harmonic, and so on. It goes up to the 7th. So you can see the same points of time, that is, you can see the waveforms of fundamental, second harmonic, third harmonic, just to visualize it. So the same thing we will visualize in the case of 2-dimensional as well, as an images, as the images basis function, this k equal to 0, 1, 2, 3, and we're varying that in the image how this basis function looks like, because this is for the 1D DCT and DFT basis functions. Now coming to the 2D DCT, 2-dimensional DCT, whatever we have learned, the even symmetrical DCT will extend to the 2D DCT computation. So the n point x of n, now x of n1 comma n2 is n1 cross n2. It's in 2-dimensional. N point is now made n1 n2 size, okay, sequence, and we have to make this 2n1 and 2n2 size of y of n1 comma n2. So as we did in one direction, the mirror image, this the mirror image should also be reflected in the other direction. So this is how y of n can be obtained in both the directions 2 of n1 and 2 of n2, like the 1D we did. After that, we take the 2D DFT of this function, that is y of n2. That would result in y of k1 comma k2 instead of y of k in 1D case the same way, 2n1 2n2, this size. The size is now it's double, and from that we would collect only n11 cross n2 because the sequence is n1 cross n2, and so this is the DCT coefficient. So this Cx k1 comma k2 is the DCT coefficient of x of n1 comma n2. So now how do we get y of n1 comma n2? The similar way what we had done. So x of n1 comma n2, that is retaining the n1 cross n2 samples, and then in n1 direction take the mirror image, that is 2n1 minus 1 minus n1. So this is representing the mirror image in the n1 direction, and if you see that n2 is kept as such, and then here n1 is kept as such, and n2 direction we take the mirror image 2n2 minus n1 minus n2. Okay, and this is extending in the next n2, and both the directions 2n1 minus n1 minus n2 comma 2n2 minus 1 minus n2. So this is n1 and n2, both the directions. So this is how we get y of n1 comma n2, which is four pieces of x of n1 comma n2 joined together. So we'll see that in this case. So this is suppose the x of n1 comma n2, which has some sample values. So it is given some instead of number, it is given in the different shapes n1 and n2 are. So how do we form y of n1 comma n2? So in this case we have this is x of n1 comma n2 and extend it to the n1 direction and then to the y1 direction, that is the mirror image in these cases, and then both the directions, that is the fourth one, which is y of n1 and n2 direction. So we have the fourth piece. So stitching this fundamental piece into other three, one in this direction, another direction, and both the directions. So this is now y of n1 comma n2, and compute the DFT of this 2D DFT of this sequence. That then it would have 2n points. So in this case n1 equal to 3 and n2 equal to 4. 1 2 3 4. So we would get this accordingly, that what is the direction. So what are the samples we would get? n1 and n2 will be different if we have n1 3 and n2 4. So how do we also we can visualize it with the periodic sequence as we did in 1D DCT. So the periodic sequence we can see that this is the first x of n1, and it is getting just repeated over here and in the x direction as well as in y direction. I have just shown these three portions. So this portion here as well as this side, and here everything is going to be just a replica of this. It's not a mirror image, and it's just a replica in the one point, and then this here as well. So this is x tilde. You have this periodic sequence. So similarly from y of n1 comma n2, that is a mirror image which we can see from here. So here this portion. So what is the advantage of doing this or visualizing this? If we see x tilde and y tilde, the discontinuities would be removed. The discontinuities won't be there in the cases of x and y. If you make it y, the mirror image, that discontinuities are getting reduced. So this is the visualization of repetition or the periodic sequence of x, which is done in both the directions, as well as this is for the case of y of n. Okay, so y of n and its periodic sequence. Getting the mirror image here. So that was the case, the smaller ones we had. So mirror image, and this is this side, and this at both the directions. So this is y of n, and that is repeated here in all these cases. So you can build up the bigger and bigger images through this pattern. So now x tilde and y tilde is not required for this 2D DCT, but to visualize it, the way in which that is obtained. So x can be obtained from x tilde can be obtained from x, and those things we had seen in the DFS, discrete Fourier series. So the 2D DCT now compute DFT of y of n1 comma n2. Okay. So this 2D DCT, after this y of k1 k2 are obtained, from that we can get the DCT coefficient Cx k1 comma k2 by multiplying both the directions W 2n1 k1 by 2 and 2n2 k2 by 2. So this for 1D we had only wn k by 2. Multiply it and collected only the k of n samples. So here both the directions need to have k1 and k2 of 0 to n1 minus 1 and 0 to n2 minus 1. So this way the DCT coefficients can be obtained, 2D DCT. So taking the 2D DCT equation, how do we get the DCT pair? So Cx of k1 comma k2 is, this is nothing but y of k1 comma k2. Okay, so we can have y of from k1 k2 we can have this multiplying w on both the sides, we get Cxk. So given a sequence for x of n1 comma n2, this would be 4. In the case of 1D it is 2. So you have the basis functions in n1 and n2 directions summation. So this is the DCT formula to compute the coefficients. Once we have this coefficients, how do we get back the signal or the 2D sequence? So having the coefficient, so these are the basis function again. The W, if you remember, a constant is multiplied for k equal to 0. This was 1 by 2 and other values this is 1. So similar thing would be applicable here as well. So for k equal to 0, it's 1 by 2, k2 equal to 0, 1 by 2, other values it is 1. So that would be used in this equation. So this is the inverse DCT. So computation steps, to summarize the steps of this. Step 1 is taking this two-dimensional sequence, n1 direction take the mirror image, n2 direction take the mirror image, and both the directions take the mirror image, add them, get y of n1 comma n2, and take the DFT of this to n1 and n2. This need not be square. N1 can be, like in our example it is 3 and this was 4. So we take the 2n point DFT y of k1 comma k2 and then multiply that with the total factors of 2n1 k1 k2 to k2. So get the DCT coefficients. This is for 1, and this especially when we multiply, this is only for the case of n1 and n2 samples, the DCT coefficients, which is also equal length of x of n samples. So these are the 3 steps. And inverse DCT, once we have this coefficient, we have to extend that to all the 4 patches what we had. So y of k1 comma k2, so what we do is for the n1 and n2 samples, we have the minus k1 and k2 similar to the 1D, and we have extended only to n1 plus 1 to 2n minus 1, and here 0 0, this is for one direction, and next y of k would be for the next direction, and this is for both the directions. So and it is n1 n2 values, it is 0, either this or this, any one of this. So this y of k will have 4 types of this. You will have Cx k1 k2 and k1 2n1 minus 1 and k1, and k1 2n2 minus k2, and this is in both the directions. So this y of k will have all these 4 of them, 4 patches, and then take the inverse DCT of this. That is step 2 is y of k1 comma k2 getting y of n1 n2, and for the this DFT computation is 2n1 cross 2n2, and then step 3 collecting only the n1 coefficients and n2 coefficients in the both the directions, y of n1 comma n2, from that get x. So these are the steps used in the DCT. So in case of the discrete cosine transform, we had learned how do we get the even symmetrical DCT by using the DFT. Even symmetrical DCT especially used in the energy compaction problems of the image coding. If this provides the energy compaction property. Also you can see the mirror image how we have got y of n from x of n, and computing the 2n point DFT. From that 2n point DFT we collect only the n coefficients, that's nothing but the DCT coefficients. So the same idea is extended to 2D DCT as well. So once we have the DCT coefficients, how do we get back the x of n, the inverse transform also we had seen. So we'll apply these DCT 1D and 2D DCTs in the on the images and get the DCT coefficient, how this DCT coefficients are helpful in image transmission. So how do we get the big larger size image, and then getting into pieces, and these pieces are coded and then are getting the coefficient of it and then transferred, and at the receiving side how it is going to be again interpreted those coefficients and getting back the image. So this is the application on the image transfer. So we would see that in the coming lectures. Thank you.